Hello. So I'm Steve Taylor. We introduced ourselves earlier. So I'm a mechanical engineer with a local firm, and then I also heavily involved with ASHRAE. If you get the ASHRAE Journal, you might have read some of my columns. I was a columnist for a long, long time, although I just wrote my last one, so I'm going to be fading away in the writing of ASHRAE Journal articles. But I've been involved in standards at ASHRAE for a long time. I was on the Energy Standard Committee when I was young, in the early 80s, and still on it now. The indoor air quality standard, the thermal comfort standard. I've been involved in a lot of these standards. And one of the technical committees is controls I've been a member of for a long time. And the idea of Guideline 36 came up probably 15 years ago, and we've been developing it ever since. And I'm going to, has anybody ever heard of it? Okay, good, a few people, that's good. And it was good to hear everybody's got sort of an HVAC technical background, because this gets pretty technical. So let's get started. So here's the agenda. I'll be talking about the Guideline 36 and its original goals and what we hope for it to become, and sort of its genesis as well. And then I'll go through some of the control logic in the guideline. It's 150 pages long, so obviously I'm not going to go into everything. And that's just the beginning. So, I mean, we're just, right now the guideline only covers VAV systems. And we're going to be expanding it to basically cover everything eventually. And then I'll talk a little bit about implementing Guideline 36. That's sort of targeted towards design engineers, but I think you all as teachers could really help in this regard as well. I'll explain it, but we need a little momentum going on this thing, and so need people to start actually using it. And then we're going to go over to the HVAC lab, and we'll do a little live demo with one of the control sequences, which is a static pressure set point reset using trim and respond. So here's what the guideline is. It's high performance sequence of operation for HVAC systems. As I mentioned, right now it's limited to VAV systems, but it's going to be expanding. We have a research project that's just finishing that has central plant, hot water, chill water plants. We have another research project that's on dedicated outside air systems and other things. So it'll keep growing over time. So our purpose is to provide uniform sequences of operations for HVAC systems that are intended to maximize system efficiency and performance, provide control stability, and allow for real-time fault detection and diagnostics. And it covers all HVAC systems. It says on there that the last line is we're also includes functional tests in there. We haven't done that yet, but ultimately we're going to be getting into that. We have another research project while I'm on that that we're doing through the state of California to come up with some testing that would be used by the manufacturer. So everybody's familiar with BACnet, I'm sure, yeah. BACnet has BTL, BACnet Testing Laboratory, and they have these testing mechanisms that allow you to test your product to see that it meets the BACnet standards. And our intent is to do the same thing here, that you'd be able to test your implementation of the Guideline 36 sequences and get a pass-fail out of it. So we have a project working on that. So part of the genesis of this was this dichotomy between configurable and programmable controllers. When DDC first started, we first started with configurable controllers. So these are controllers that the logic's burned into it. For those that are used to lawn systems from a while back, they mostly followed this philosophy. We're just going to burn the sequence into the thing, and all you can do is configure it. You can change the CFM set points and other things, but you can't actually change the logic. And then we have fully programmable controllers, and most of the early companies that jumped onto the BACnet bandwagon started off that way. There's nothing inherent in BACnet that says you can't use one or the other. It's just the way the industry developed is that the new BACnet people tend to do fully programmable. So you could do whatever you want. It was sort of a blank slate. See, the advantage of the configurable ones was that they're all plug and play. So you could just put the system together, plug it in, and arguably it works. And that's really nice. So it reduces your installation time, commissioning time, and reliability. Unfortunately, in general, the sequences were really simplistic. In fact, the early DDC controllers simply implemented a pneumatic control. You know, if you look at VAV boxes with a pneumatic control, the early DD systems, they did exactly that, no more. So it was basically an expensive pneumatic controller. And you can't change it. You know, so when Guideline 36 comes along or something else comes along, sorry, it's burned in there, you can't change it, this is all you get out of the thing. And many of them don't even meet codes because the codes are constantly changing. And if it's burned in there, obviously it can't keep up with the codes. So it doesn't meet 90.1 or ASHRAE Title 24 in California, and it never will because it's burned in there. Now, it doesn't have to be that way, but that's the way historically it went. So with the programmable controllers, we can do anything we want, and that's great. But seldom do we actually do a good job with them. You can program whatever you want, but it's awful simpler to just do what you did last time, use the default from the factory, maybe use what the engineer provided, but as a consulting engineer, I'm allowed to criticize myself. Engineers suck at writing sequences, you know, and most controls people completely ignore what's on the drawings and specs on a job because they know that they're nonsense. And they can do what they did last time way much faster anyway, so it's just never used. And often we get poor programming by the contractor. We have market pressures to get off the job. And I heard on the bios, a couple people talk, they were used to work for a controls tech. Who's the last guy on the job, right? It's a controls person, and they're often a sub to the mechanical, and the mechanical's beating them on the head, said, "You're done, come on, I want to get paid." And they often have to sort of leave early when they're not really done, just to make everybody happy. And they're often poorly commissioned or not commissioned at all. Fortunately, a lot of the codes are changing to require commissioning, but commissioning can be like balancing. Everybody heard of drive-by balancing? We now have drive-by commissioning too. Fill in all the forms, hand it in, never go to the job site. And so it doesn't necessarily mean that it's good. Whenever we're required to do something, the marketplace will take us down to the lowest level. And then often poor training by the building engineer. Back in the old days with pneumatic, all the controllers spoke the same language, right? 3 to 15 PSI. And when it came to DDC, it got a lot more complicated, and a lot of times the building engineers weren't able to keep up with it. Other issues with controls today, we keep reinventing the wheel. We have one VAV box, and everybody does it differently. So here in Oakland, we have hundreds of buildings. Most of them are VAV systems, and I can assure you that almost every one of them uses a different way of controlling a VAV box. You know, it makes no sense to do that. We don't keep up with the codes and standards. I've been involved with Title 24 and 90.1 and 62.1 for years. I can tell you they're always changing. Every 3 years, they republish something and they change. And you have to keep up with that, and it's really hard to do. To keep up with all these standards. They change so frequently, and most people aren't aware of their changes. It's not like they're in the newspaper. So it's difficult to do that. We don't keep up with research projects. I mentioned that we're doing research projects. We're a consulting firm, but we got into doing research with ASHRAE in part because we weren't happy with the research projects that were being done at ASHRAE because they're all designed by professors. So they wanted to know, you know, what's the characteristic of R134A boiling on a flat plate, you know? I couldn't care less. What I want to know is how buildings really work, you know? And so we got involved with ASHRAE to write work statements for research projects. And then we started actually bidding on some of them ourselves when they related to controls and things that we knew. So we're involved in them. Now, all these research projects are all controls-related research projects. And almost all of them have gone into Guideline 36 to improve their performance. And let me tell you, it's impossible to keep up with all that stuff. It's just impossible. Another thing that's totally underutilized is alarms and diagnostics. We either have too few or too many, right? So if you have too few, things can go wrong and you don't know about it because there's no alarms. Too many is when it alarms on everything, you know, and it's constantly giving you an alarm, and pretty soon you ignore it. You know, it's like the signs we always have that say there might be some nuclear fission in this building and it's going to kill you, and we all just walk right by it, right? And same with alarms in buildings. If it's constantly alarming, we just don't listen to it anymore. Neither is effective, so we need to improve that. All right, So moving on to, so all the problems, here's another problem, is we have the KISS principle, keep it simple, stupid. And the old paradigm was building engineers will disable things until they get it down to their level of understanding. So you really need to keep the sequences simple or they're going to be destroyed. And that just doesn't work these days. The new paradigm is we can't afford to do this. So if Steve Jobs thought, I'm going to make a really simple phone, and we'll all be happy with that. We'll call it a flip phone, Everybody's going to like that. No, he didn't say that. He's going to make something that is so freaking complicated, but the interface is simple. So now KISS means keep the interface simple, but underneath we want a Ferrari. Underneath we want something like an iPhone that is incredibly complex underneath, but the interface that we have to it is simple. So the example again is like, think of a car. Nowadays you don't work on your car anymore. You lift up the hood, and of course sometimes there's nothing under the hood. It's electric. But the car is super complicated, and you don't care as long as when you get into it, it goes. And it's all been optimized. Well, we need the same thing with buildings. We need to make the building just go so that the building engineers don't have to disconnect things and don't have to break it. They're going to be busy doing what other things that happen in the building, and they don't have to watch the controls because the controls will actually work and they'll be optimized. That's the big picture goal of what we want. All right, so this is the goal of Guideline 36, was to merge the benefits of the configurable controllers with the benefits of the programmable controllers. So we're going to be able to be fully debugged, plug and play, ready to go, but we're going to have sequences that are super advanced, that meet all the codes and provide reliable performance. That's the goal. So here's how we think it's going to be maintained and work. First of all, we have this committee, the Guideline 36 committee, and it's responsible for creating and maintaining the sequences. If you're familiar with ASHRAE committees, people are allowed to make code change proposals, or in this case, a guideline change proposal. So if you have a sequence that you like, or you've used some of the Guideline 36 sequence and you think you can do it better, then you make a proposal. The committee usually hones the language a little bit and either adopts it or not. It goes out for public review and then eventually gets adopted into the guideline. As we do the research projects that we're doing, all of those now, we make the deliverable of the research project actual control sequences, and also in a flowchart formula so that we don't have the normal misunderstandings that the English language has. When you do sequences, you need English because somebody, like the building engineer, has to understand what's supposed to happen. But you also need a logic flow diagram because our English language is inherently inaccurate and whatever. So, and then the manufacturers will test it, pre-program, and do everything for their dealers. The engineers say, just use the Guideline 36 sequences, so no longer do you have to write sequences and spend that time doing it. Controls contractors say, hey, great, I've already got those programmed. And they put them in. And then the commissioning agents say, oh, perfect, I already have functional tests for those sequences. So it's a total win-win-win for everybody. It's less time for the building engineers, less time for the controls dealers, less time for the commissioning people, and the building owner benefits the most by getting a system that really works and works really well. And I'll show you some test data that we've done on that a little bit later. Eventually, you might even forgo commissioning. Just say, hey, these things were tested in the laboratory, like BTL for BACnet, and say, hey, it's supposed to be plug and play. Let's just see if it plugs and plays. Now, I don't think we'll ever quite get to that level. Unfortunately, with our buildings, it's not like cars. Cars, they build the same car over and over again, and buildings, we build one building at a time, and they're all unique. All right, so our goals: reduce costs for sequencing, program commissioning, reducing errors by eliminating ambiguity, knowing that the algorithms are tested and standardized. We ensure that all of our codes and standards are complied with. And we improved energy efficiency and indoor air quality accordingly. And we improve reliability and ease of operations. So one of the things we have in the guideline that I'm not going to really talk about that much is the alarms and fault detection. So it's amazing, you know, our controllers are fancy little computers, and we use a tiny, tiny percent of them, right? Probably like most of us on our phones, you know, you use like 10% of its capability. Our DDC systems are the same way. We don't use enough of it. We can build in diagnostics and fault detection into our controllers right now. And by doing that, you can get a lot of the benefits of fault detections where it says, hey, this valve is stuck open, you know, and you can go and fix that. So we have that in there as well. All right, so I'm going to go through a few of the example sequences, some of which you probably are familiar with. One of them is called dual max. So anybody heard of this? So this is VAV, for those of you doing VAC systems. This has been around for a while. I wrote an article on it in about 2002 or something like that. It got incorporated into Title 24 in 2003 and 90.1 about the same time. So it's been around for a while. The idea is that a traditional VAV logic is you have a minimum. So you're cooling, as the cooling load goes down, the airflow goes down, then you hit a set point, and it doesn't go above or below that. And then you do all your heating at that set point. And so this purple area is sort of representative of reheat. And you want that area to be as small as possible because that represents inefficiency. So with dual max, we go down to a lower minimum. And that minimum can be really low, and I'll talk about more about that later. But it can be really, really low. We first try to heat with that low minimum by raising the supply air temperature off the box. And then once we get to a maximum supply air temperature, we don't want it to get too hot because then it stratifies if you're overhead heating. And so you let it only get to about 90 degrees or so. And then if you can't heat there, then you make it go back up again. So the idea is that this now area below the curve is smaller. Again, the energy standards required this for a while, but it takes a while. As an example, I do a lot of peer reviews. I'm in the CSU Mechanical Review Board, and so I peer review all the Northern California campuses. And that requirement in Title 24 got in there in the 2004 version, I believe. And so that was a long time ago, right? In order for this to work, you need 2 set points. This has 1 set point, 2 set points. This has 3. 1, 2, 3. So your VAV box schedule has to have 3 columns in there, you know, heating max, cooling max, and minimum. And even as much as 2 years ago, I get drawings that only have 2 columns, you know, and it's been 16 years since it's been code. People don't do a good job, you know, that's why we try to automate these things. In Guideline 36, it's actually a little bit more complicated than that. We have all these endpoints that can change depending on which mode you're in, occupied, cool down, warm up. We can flip these numbers around to improve performance. We have sort of a minimum plus cooling heating minimum. This allows you to do like electric heat that might have threshold for airflow before the heat will come on. So all kind of stuff. So it's even more complicated than the other figures, but the result is about the same. We did a research project called RP1515, which we did jointly with the Center for the Built Environment, UC Berkeley. And the idea was to test whether this dual max sequence actually worked in the field. People had concerns that, wait a minute, you're dribbling air into the space. You're dribbling it into the space. Isn't that going to cause stuffiness? Isn't that going to make people unhappy? And the stratification can be worse. I mean, does this really work? It works theoretically, but does it work in real life? So we did a research project to test it, and we did 8 campus buildings for Yahoo, and then another state office building, and we changed the sequence where we went from 30% minimums, which is the Title 24 number at the time, conventional logic, and then we'd flip it to dual max logic, and we do it randomly over an entire year. And the people, after it would switch, maybe the day after or something like that, it would pop up to these little screen things to people who volunteered for it, which was almost everybody. They said, you know, are you comfortable? Would you like it warmer, cooler? You know, can you feel a draft? All these questions about comfort. At the same time, we were keeping track of the energy use of the building when it was on the new sequences versus the old sequence. So it's a perfect experiment for intervention because it's got the control group is the same group. And one of the things that came out of that is that our loads are really low. So we think of, in the old days, 1 CFM a square foot was like a rule of thumb for cooling loads in a building. We're not anywhere near that in general. This is for all zones in the building, so only a handful of zones would ever get up that high. This could be like the west zone or something that's getting up that high. But most of them are way down in here. And so most zones are well less than a half a CFM per square foot in terms of their actual loads. Now, why is this? Because we have LED lights, we have computers that go to sleep, we have laptops instead of desktops. All of our loads are going down, 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 and all of our controls are getting better with it. We have occupancy sensors that turn off the lights when we're not there and make our computers go to sleep. Everything is going down, which is beautiful. But our VAV systems weren't really designed for that. So here's the same project, and here's the frequency of the percent CFM for all the zones in these 6 buildings, or 7 buildings. And so you see that the conventional logic was 30%. That was what the minimums were. But you'll see that the minimum's also the maximum, right? It never went above 30% except for just a little bit. And then some warm up and cool down extremes over here. But basically speaking, the boxes were 3 times bigger than they needed to be. Now this is normal, because we engineers are conservative, and when we design a VAV box, I'm going to assume all the lights are on and all the people are there and the blinds are open, and I'm going to do all those things because that's just the nature of the beast. But when you use a percent times something that's oversized, it's oversized too. So the Guideline 36 logic had the minimum set to the ventilation rate. And so it's a broader number in here, but you can see how much lower the airflow rates were in the building because the loads are so low. Everything got pushed to the left. And so all the airflows went down, and you can see that from 5 to 10, what is it, about roughly 12% maybe average for the building in terms of the airflow. So they all went way, way, way down because the loads are way, way down. So right now, Title 24 says that if you have DDC, your box, you have to use dual maximum logic, and the minimum can't be bigger than 20%. Okay, well, that's better than 30%, but it's still too high because you can see 20% right here. So if you had required 20%, this whole little blue thing would shift over the 20%, and we'd still be wasting energy. So we're not using percents anymore. 90.1 passed an addendum that says the minimum shall be equal to the ventilation rate, period. And it's not a percent of anything. It's what the ventilation rate is, and that's all you get. Title 24 has one pending that won't show up until the next version of the standards in 2022, but it'll say the same thing. So back to that comfort issue, we looked at the different buildings and how happy that people were, percent dissatisfied over here on the left. And you can see that the conventional logic had way more people dissatisfied than the new logic. So we were just hoping to break even on this, right? We were just hoping that nobody would notice that the airflows were changing. But in fact, it was better than that. We improved comfort. In every building, the comfort got better, particularly in the warm season. Now, why is this? In the warm, I think we're all familiar with overcooled buildings, right? It seems like when you go to a convention center, it's always that way. Everybody's in sweaters, even though it's 90 outside. We overcool buildings. Now, in convention centers, they're just crazy and they put all the set points too low. But in normal buildings, we see the same thing. And partly the complaints are that in the summertime, I'm not wearing heavy clothes anymore. And we get this. So over on the left is a conventional logic. So here's my logic. I reduce the airflow as the load goes down. Let's say that I had a certain load that required this much CFM with this red line. That's what I needed to match the load. If I had conventional logic, I would go down to a minimum. It's still too much air. So it pushes me into heating. And I finally satisfy the load right over here where I'm in the heating mode and the hot water valve is open to keep the space from getting any colder. So what's the temperature of the space? It's now 70 or whatever my heating set point is. If I have dual max logic, it goes down and goes, oh, perfect. I'm happy right here. You're in the cooling part of the logic, so the space is 75. So here I am in the Yahoo building. I'm wearing a t-shirt and shorts. And 75, I'm peachy keen happy. 70, I'm freezing. And that's exactly what we saw. So the moral of the story is we want everybody to set their minimums, not to some arbitrary percent, but to the actual ventilation rate. So our VAV Box schedules, which used to have cooling maximum, heating maximum and minimum, will now also include other numbers in there, like the ventilation rate. Now we use, in Guideline 36, we use the ventilation rate at the zone level in part to reset the ventilation requirement at the air handler. How many people have air handlers that serve what we call zone groups, which are like you can serve part of the building but not the whole building, right? That's been in the code since 1991, often overlooked. But if you have a system that's bigger than 25,000 square feet, you have to break it into zones, groups of zones that have different schedules or have the capability of different schedules. Well, when you do that, the airflow you need for ventilation is going to go down when only one of those zone groups is occupied and all the rest are closed. Well, most systems don't have that capability, right? They don't know that the ventilation, so you over-ventilate those spaces that are occupied at that time. Well, we don't do that anymore. We actually collect the airflow information from the zones and pass it up to the air handler, and it says, here's what your ventilation rate is. It's only the ventilation rate required by the zones that are there. And then for those familiar with Standard 62, our ventilation effectiveness is a function of the supply air temperature. So if we have warm air, it tends to stratify, doesn't mix as well, and so I need to account for that. And for cooling, it works great, so I don't have to. And then both 90.1 and Tile 24 have CO2 demand control ventilation requirements for densely occupied space, like the space here, where we can reset the ventilation. So that minimum now is simply the ventilation minimum. It's not 20% of something or 30% of something or any percent of something. It's equal to the ventilation requirement. And for zones that have demand control ventilation, it's equal to just the building control component of the ventilation rate, because the people component is dynamically determined by the carbon dioxide. So I can go all the way down to the building component when nobody's there. When people start coming in, that minimum will raise up automatically because of the carbon dioxide. And then we passed an addendum last summer that says you don't even have to put a number in there anymore. First of all, again, with all the peer reviews I do, people, they're not really comfortable with these low minimums. Change is hard with some people. And so they'll fake the ventilation requirements and make them artificially high just so they can say, yeah, I'm putting it down to the ventilation. I'm assuming there's 800 people in this room, and that's what I'm going to set the minimum to. So people don't, so we like to sort of take it out of their hands. So we'll just put auto in this column right here. And if you do that, the Guideline 36 sequences will automatically figure out your minimum for you dynamically. So if the space has an occupancy sensor, like most do today for lighting controls, we backnet into that through the lighting control system. Now we know the occupancy sensor. If nobody's there, you don't get that ventilation. If the CO2 sensor says not many people are there, that reduces the ventilation as well. And if I have the space, depending on whether it's cooling or heating, I can adjust the air change effectiveness for those numbers. So I dynamically figure out what my minimum is. So it's always the lowest it can possibly be. So the first question people says, yeah, VAV boxes can't control that low. We all know that. Well, we know it because people like the major manufacturers, Titus and Price and whatever, they have these little tables and say, here's the lowest minimum you can set. It's total BS, okay? It's absolutely, how could they know what that is? Because the minimum is a function of the accuracy of the velocity pressure sensor, the transducer, and then the A to D converter to get it into the controller's language. That is one part of it. The other part is the amplification factor of the VAV box airflow sensor. However, that part is almost the same. Everybody has a factor of about 2, and that factor is constant, goes all the way to zero flow, doesn't matter. So the only thing that really matters is the velocity pressure conversion. And that's a function of the controller, not the box. So how does Titus and Price know what controller you have? They don't. So they set a very artificially high number, and it's wrong. Okay, and you shouldn't ever use it. So people didn't believe that either. So we did another research project, RP 1353. This is what I love about research. What people have all these old wives' tales. You know, you can't dribble the air in, it dumps, it does all this kind of stuff. And we say, really? Well, let's try it. You know, let's see if that's real. When we tested this one, all the airflow manufacturers, all the VAV box manufacturers said, our flow cross, when it gets down to really low, it doesn't amplify anymore. It just falls apart. We said, oh, really? Okay, well, let's just test it. So we tested in there. Every single one of them went all the way to zero with the same amplification factor as it had at high velocity. Perfectly linear, all the way to zero. And all of them said, geez, I didn't know that. They didn't know because they never tried it, right? Because somebody told them a long time ago it wouldn't work, and they believed him. And so we do research, and we find out that that is wrong. We also found wrong is that VAV Box's controllable minimums are much higher than most people think. And so the research project showed that we could get down, this is for an 8-inch box, we can get down to 50, 40 CFM before it starts dying in terms of accuracy in here. Okay, so we tested every single manufacturer's VAV box controller there is. Some were better than others, for sure, but most of them were pretty good. And just as a hint, by the way, all of them are the transducers. You can hear, there's two types, a diaphragm type and a hot wire anemometer type. You know, it's basically using airflow across a hot wire thermal anemometer. The thermal anemometers work way better than the diaphragm ones. But almost all of them could measure down to 0.003 inches velocity pressure. In that Titus catalog, it will catalog this thing at 0.03, 100 times or 10 times more, a full order of magnitude more. And that's just, you don't need that. We can do way less with that. And then controllable minimums is a little higher than that because you need to have error on both sides of the point. So it's about 0.004, and virtually everybody can do that. So using the 0.004 and some fundamental equations here, you can end up where roughly the controllable minimum is between 8 and 12% or so of the box max. It sort of depends on how you size the box. But we did another research project where we found that sizing it for 0.5-inch total pressure drop was life cycle cost optimum. So starting with that, we can end up where the minimums are between 8 and 12%. So it's way lower than what everybody else thought over the years. Well, then what happens if we have a really low ventilation rate? That can certainly happen. What happens with that? Well, we have another thing to take care of that. Timed average ventilation. If the ventilation requirement is less than what your controllable minimum is, we pulse the air into the space. So Standard 62 and Title 24 allow you to time average. So you don't have to have the ventilation completely constant. You just have to have it right over a time period. And the time period is quite long. For a typical office building, it's about 6 hours. Most people don't know that. So you only have to be right over an average of 6 hours. Leaves you a lot of flexibility there. Title 24 doesn't use the same equations, but it lets you average over an hour. So in Guideline 36, we made it 15 minutes, just to be super conservative. So what it does is that it pulses the ventilation in. So like if you wanted a desired set point of 100, but my controllable minimum was 300, I would pulse in 300 and then do nothing for 2/3 of the time. So 1/3 of the time I pulse in 300, then I do nothing for 2/3 of the time, and then I pulse in 300 again. So you don't have to measure zero, so there's no issue there. So this is the controllable minimum, and this is just zero. And I can make it any set point I want. So of course we have to test it, right? Because the same kind of argument, well, aren't people going to notice, this psh, psh, Well, the fact is you're already dribbling the air in, right? So it's not going to make any noise. And we tested it, and nobody could notice, not one person noticed that we were pulsing the air in anywhere in the test. However, we did find a flaw in our sequences, is that because loads are so low and we're often at the minimum all the time, We ended up where all the boxes closed at the same time, and that didn't work very well. So a fan tripped off in high static. I think we blew off a flex duct or something. It's like, okay. So we have some added logic that randomize, so to pass a token that says, okay, you can go down to 0, but the other guys can't, to try to make it so that not everybody goes down at the same time. All right, so set the box to the minimum ventilation rate. You don't have to worry. Oh, don't even worry about that controllable minimum, by the way. Guideline 36 says, you know what? Since the manufacturers publish bogus numbers, and you as the designer, you may not know who the controller manufacturer is going to be, right? It's going to be put out to bid, and maybe it's going to be different from who you designed around, and you don't know who the VAV box manufacturer is going to be either. But by the time the job is ready to be commissioned, the controls contractor does know these things. It's his controls and that guy's box, and you know all the information you need to actually calculate the controllable minimum. So Guideline 36 puts it into the hands of the installing contractor to figure out the minimum. So the engineers don't have to worry about that anymore. Just set the box to the Title 24 minimum or 62.1 minimum, depending on where you're in the country. By the way, Guideline 36 has both Title 24 ventilation requirements and 62.1. So you just click a box and it will pick up all the right codes in there. Or you can either set it yourself to those minimums, or better is to set it to auto. And then it automatically determines the minimum dynamically. So it's even more energy efficient. And then the Guideline 36 will automatically use TAV if it needs to drop the control to that airflow. So if anybody has any questions as I'm going along here, jump in. All right, so now I'm going to talk about another sequence, which is supply air temperature reset. So again, this is a VAV system. If you make the air colder, then all the zones that are in cooling need less air, so my fan energy goes down. That's good. But sometimes I can end up doing more reheat, and I lose my economizer capability. So if I make the air warmer, just as warm as it needs to be, I can extend my economizer's capability of delivering 100% of the load. And I can reduce reheat at the zone level. So you have this balance. So in the past, people thought, you know what, I should always make it warmest, the warmest temperature that the zone that wants the coldest air can handle. Warmest zone logic, people call it, or because that's what the energy programs call it, warmest zone. And in fact, that is not the best way to control a VAV system, because fan energy is a big component of this thing. So to find a balance in there, we look at both warmest zone, trying to figure out who's the warmest zone, and we use this logic called trim and respond. How many people know what trim and respond is? Okay, one or two. Trim and respond is a mechanism for, I'll talk about it in more detail in a minute when we talk about static pressure set point reset, but it's basically a way of figuring out, like in this example here, what's the warmest zone that'll satisfy the zone that needs the coldest air? How do you know this? Well, in a computer program, it's real easy. I calculate the load in the zone, I divide by 1.1, and the maximum CFM of that zone. That gives me a delta T. I add that to the room temperature, subtract it from the room temperature. Oh, there I go. I need 62.1 degrees to satisfy that zone. And now I know my set point is 62.1. In real life, we can't do that, right? We don't know what the loads are, so you can't get there. So what we do is we just sort of gradually say, does anybody need colder air? No? Okay, I'll make it a little warmer. Does anybody need colder air now? No? Okay, I'll make it a little warmer. And that's called trim and respond. And then somebody said, yeah, I need colder air. You say, okay, fine, and you drop it down. So, and we do this with all the resets, because it's basically the only way we know how to do it. And I'll show you in a few minutes. It's not perfect way of doing it, and somebody can probably come up with a better way of doing it, but it works. All right, so we have trim and respond for the warmest zone, but then we say, okay, we know that fan energy matters. How about we envelop that with a outside air temperature reset on top of it, so that particularly when it's warm outside, I deliver colder air, because then I know I'm not doing a lot of reheat at that time. So I have this logic that ends up with, in colder weather, I have the warmest zone taking care of it. The economizer is maximized, reheat is minimum. In warmer weather, I have cold supply air, so I minimize my fan energy. And here's what it sort of looks like in a graph, I'm doing this warmest zone Tmax calculation all the time. I'm asking the zones, who wants colder air, who wants colder air? But on top of that, I override it and say, yeah, okay, you can do Tmax, but no more than this line up here, right? So and then as the outside air temperature gets warmer, I reduce that amount. So when it's 70 degrees or whatever I want outside, I'm now delivering my 55-degree air design, regardless if any zone wants it that cold, because it makes it better for fan energy. So that's the basic logic. If you do some trend logs, you can sort of see how well it works. Usually you want a big scattering of points over time, but if you have all the zones are oversized, that means that they all can handle the load at almost any temperature you give it. All the dots collect on that upper line. And then if you have a rogue zone or so, you end up with everything on the lower part of the line. I'll talk about rogue zones in a minute. Those are zones that are always asking. And I'll give an example when we get into the static pressure set point reset. Okay, more research. So we did another research project at the Berkeley campus to experiment with doing a better type of reset. So Raftery was the PI from Berkeley. The way it works is we try to actually calculate the energy of the building and optimize the energy. So we calculate what's the reheat load that's happening at the zone level. We estimate what the fan energy would be using just normal semi-cube law curves. And then we just throw in efficiencies for the chilling, cooling and heating. We don't get into part load stuff or anything. It just has a COP in it, and that's that. We're trying to make it reasonably simple so it can be implemented in a general way. So if there aren't any cooling requests, we reset in the direction of lower costs. If there are cooling requests, we give people what they want. We're not going to make them uncomfortable to save energy. So we experimented with this both in real building, and then we also did it with a simulation. So the simulation results are what's shown here. And the optimum, what we did for the optimum is we just simulated every possible supply air temperature you could possibly do every hour, and the one that has the lowest energy, that's the optimum. And then obviously you can't achieve that, so we're trying to see how close to the optimum we can get with real sequences. And you can see that warmest zone, always supplying the warmest air you possibly can, was probably the worst in terms of, by the way, all these different simulations here are just because when you do a simulation of a model, that's not a real building, right? Chances are things are really oversized, or the pressure, static pressure in the fan is too high, or the VAV box minimums are too high, things like that. So we experiment in the simulations to see what would happen if it was an imperfect building, and that's what all these variability is. Okay. In fact, the warmest zone was actually worse than just maintaining 55 all the time, which was surprising result. And then here's our guideline 36, using two different outside air set points. So going back to this thing, this one says from 60 to 70, I'm going to slope the line down. We did it from 60 to 70, but we also did 50 to 80. And it turned out 50 to 80 was actually better than 60 to 70. So that's what we got there. And then the cost-based one is what I was describing here, and that's what we were experimenting with. And it does even better. So we're now doing another research project to generalize this to make it so that you can apply it sort of generically. One of our problems is we know people aren't going to take the time to make the control sequences like tuned to their building. So we have to provide reasonable default numbers that work everywhere, so it's plug and play. We know people aren't going to do it, so we can't say, oh yeah, to make it work, you have to optimize on this number. It's not going to happen. So we're going to do some more research to come up with some sort of generic way of making the cost-based reset work better. So we're working on that one right now. By the way, I was talking to somebody earlier. When we did this experiment in the building, when we did it in the real building, we found something very peculiar. To do the calculation, you actually calculate the reheat energy. You know the CFM, you know the supply air temperature, you know the entering air temperature from the air handler, so you can calculate the reheat load. And then we also had a BTU meter at the boiler. And what we found was, when we did this thing over a whole year, is that if you added up all the reheat loads at the zone level, they were less than half of what the BTUs being produced by the boiler was. I went, what? So the other is losses out of the system. Now, probably a lot of people have seen when somebody insulates a reheat coil, and this was the case here too, somewhere along the way, somebody decided that they didn't have to go past the hot water shutoff valve. Everything beyond that is bare, you know, and it just becomes standard practice. There's nothing in the code that allows that. In fact, we just put in language in Title 24 and 90.1 that describes what the piping system is and includes every piece of pipe that the water goes through. So you can't do that. And hopefully we can enforce that and get people to not do it. You know, heat losses are not linear at all. You know, just because you insulated 90% of the pipe doesn't mean that you only have a tiny bit of losses. They're nonlinear, and so those bare pipes are just radiating energy. Now, not all that's lost, right? Some of it might warm up the ceiling a little bit and conduct down into the space, and so maybe it's not lost. But then again, some of it warms up the return air, and now I'm cooling it. You know, so serious issue that we came up with that one. So we're doing another research project to quantify that to see how big of a problem it is. All right, just moving on a little bit to economizer controls. So everybody knows what an airside economizer is, no doubt. The traditional logic on an airside economizer is that as you open the outside air damper, you simultaneously close the other damper, the return damper. And if you do, there was an interesting research project that somebody did that found if you had parallel blade dampers, the mixing box differential pressure was fairly constant if you use parallel blade dampers. But if you use opposed blade dampers, at the 50% point, the pressure drop was like double, more than double what it was when the dampers either all open or all closed. And the reason why that is that if you think of an opposed blade damper, at 50%, it doesn't have a lot of open area, right? Whereas a parallel one is like this, it's got tons of open area. So the percent position is not the same. So this is sort of a disaster here, right? It ends up using a whole bunch of energy for no reason at all. So in the Guideline 36 sequences, we sequence them. We open up, and at the 50% position, they're both wide open instead of both half closed. And so by doing that, the pressure drop goes way down, and since I have variable speed drives on the thing, I can take advantage of that, and I save energy by doing nothing, really. You know, it's so simple to do this, and it cuts the energy down significantly. We also, somebody said, yeah, but does it mix as well? So did another research project on that, and found that it actually mixes better, because now the two airstreams are sort of blowing straight, you know, as opposed to sort of getting deflected by the vanes of the dampers, and so it actually mixed a little better. But when you're at 50%, mixing doesn't really matter usually all that much, right? That's when the air is not that cold.